All right. Well, good morning.
Good morning.
August 3rd, 2025. And welcome to the Cosmology discussion group. We're going to talk about cosmology today for a change. Isn't that interesting? Vladimir is going to talk about magnetism. Magnetism, that should be interesting. Magnetism is kind of important in the universe. There's a lot of magnetism going on all around the universe. We have magnetism on the Earth. We have magnetism on the sun. We have magnetism in the centers of the galaxy. We've got magnetic fields, lots of different places. Okay, I'm waiting. We're a little early this morning. I'm waiting for other people to show up. Do you have any comments or anything you want to talk about a little bit while we're waiting for other people to show up?
I'm ready to start, but let's wait for a couple more people because it's very important for them to feel my emotions, my attitude, my presentation, why I'm talking about, and what is going on with this theory, with this effect, with this phenomenon. That okay,
Okay.
Jan here, French is here. No, at least we can start.
All right. Well, I guess we can start. We got Ian now, and I see Robert French is
Yeah,
on.
yeah.
Yes, yes. And maybe later we will discuss yesterday meeting with you, Ian. I promised you, but let's finish our business today, our business, and then we'll come back to your business yesterday. What is our opinion about general relativity and collapse of it?
All right. Well, before we start, I want to make a little advertisement. I, many years ago, got interested in this was in the middle of the 1990s, I guess it was. I got interested in the history of electricity and magnetism. And I collected a lot of books on this subject. And what I discovered is, contrary to what a lot of people say, magnetism is probably the oldest science, except for maybe astronomy. It goes all the way back to the Greeks, and
Exactly.
it's a very, very interesting topic historically to research. And I have a number at the General Science Journal. I have written about magnetism and the history of magnetism. So I'm very interested in what you have to say about magnetism today. So if you'd like to go ahead, your topic is magnetism and the world universe cosmology. So go ahead.
I will start, and what is important, I will show you the same paper I sent you guys yesterday to be prepared maybe for this talk because it's a little bit more difficult than usually because I will use some equations, some ratios, something like mathematical, and I know that people doesn't like mathematics. That's why
We're
I
supposed to
sorry
be
that
doing science.
yes, it's exactly today. It's a scientific. And what is important, we will discuss with you the nature of magnetism, the fact that well known for many, many years, 1,000, 2,000 years at least, and that the field that, in my view, up to date doesn't have a true nature of physics, true theoretical foundation. I invented my Dirac particle. It was a long time ago, 24 years ago. And then I published the first papers. I named these Dirac particles many times. And what I had in mind, I will tell you today because it's already so many years past. In couple papers, I put this Dirac in game, in place, and I told something about it. But today I will concentrate only on magnetism to talk about it, why I put this Dirac particle, what was the meaning for it. And then, you will understand why I put this LO Dirac as a so-named dark matter particles, but now by the way, thanks to Harry, it's universe created particles. Remember, 1.5 years ago, we talked with you about. That's why let me start my talk with the same
All right.
paper, but I will
Before
give
you
you all
start,
the comments. I will give you
before,
the comments during this, talk. And then after I will finish, you will ask any questions about magnetism. I'm ready to answer.
all right, before you start, tell us a little bit about, well, what does I guess I'm not sure whether you call him a Dirac particle. Dirac, is that his name?
Or maybe it's a Russian pronunciation because I used to Dirac, Dirac, maybe Dirac,
I'm not
because it's a
really sure.
French name, by the way. I don't know how to pronounce in English or
I
in
say
French.
Dirac, but yes.
Huh?
I say Dirac, but
Yeah.
Me
Dirac is
too.
probably the more
The
common, I
European
think.
guy.
The French, yes.
Okay, so you named your particle after the famous physicist P.A.M. Dirac, and that's correct, right?
Yes, it is correct. But what is the point? It's not named behind him. I use his monopole, that Dirac idea.
Okay,
And
right.
you will see it plays. I changed his monopoles for dipoles. And of course, I followed name Dirac because it was his great idea about 100 years ago, by the way.
So
All of this
your
well known.
particle is a Dirac dipole. So you've
Yes,
changed his monopole into a dipole.
yes. Let me, I have to tell you about my understanding of this Dirac, and you will understand it. Everybody knows some magnetic compass, I suppose I pronounce the right way, compass, with some needle, magnetic needle inside. And we can see where is our north pole of Earth with this magnetic needle. But tiny Dirac, it's a tiny needle, magnetic needle. That's it. That's why have in your mind right now this needle in compass, and I will follow this simple idea everybody knows about that this Dirac, as it's a tiny the dipole because this needle dipole too. This is exactly my point. That's why it's some kind of analog what I'm talking about. Let's
Okay,
start.
we're
Maybe
ready
share
to
my
start.
screen. Yes, share screen.
All right.
Send a request. Compass, and needle. It's a tiny needle in my theory, in my model. No share. Did you?
I approved your request, so you should be
Joseph,
ready to
thank you so
go.
much. Share. Okay, where is it? Okay. My goodness. Where is it? Return to meeting.
Okay, you should have your presentation open in.
Yes, yes, I had it before I started, but let me
All
come
right,
back.
when
Guys,
you do
couple minutes, don't worry. I know what to find and where it is. Let me find it.
yeah, you have to click
Before
on
we
you have
started
to click
our
on the window where the presentation exists, and
Yes,
then
yes,
you
yes,
have to
yes. Let me
share
open this
screen.
presentation because I prepared it, but unfortunately, as your computer, my computer crazy too. I prepared this presentation. It disappeared. Where it is right now? Let me find it.
And don't forget to click share screen.
Yes, yes, I will do. Don't worry. Let me start everything from the beginning.
Okay, while
My
we're waiting, this idea of I think the fundamental um, issue about magnetism is that magnet is the magnetic dipole. I think you've hit upon that idea correctly. I think
yes, yes,
magnetic
it's the main
monopoles.
idea. The
I
main
think the
idea.
magnetic monopole is a fiction, and classical electrodynamics doesn't admit of any kind of a magnetic monopole concept. So a
Yes,
dipole makes more sense from a classical physics point of view.
yes, sir. Let's go. I loaded it and let me go to. It's
I think the only one of
unbelievable.
us who descends from that, Harry, is Bill Lucas.
And
Yes, I
where is
know,
him?
but his idea of magnetic monopole is kind of he refers to that as a refrigerator magnet, which kind of
Right.
A
Well,
refrigerator. Oh my goodness. I didn't know about it. Please send me some reference. I will do it. Unbelievable. Unbelievable.
so I don't
I don't
recognize a
have.
magnetic monopole at all. I just see it, all magnets are basically circulating charges.
I will tell you about this approach today. And it's very close to my idea. You will see right now, guys.
all right. You need to get the presentation going.
Yes, 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 I know. Let me go.
In addition to the mention of Bill Lucas in terms of magnetic monopoles, the magnetic monopole is intrinsic to the postulates of binary mechanics, which have been very, very successful.
Well, then I'm wrong. We need to add you, Jim, to the group dissenting from the principle
Magnetic
of
monopole list.
dipoles.
No, oh no, it's crazy. It's just crazy, unbelievable. Guys,
So-
I have not so long my presentation. Please talk about this, your opinion, your point, because I don't know what's going on with my computer now.
Oh.
I don't know.
Maybe
So-
Vladimir, maybe you need to stop sharing the screen you're sharing now, and then start.
Yes, yes, I agree with you. It's
Okay,
exactly my point. And I'm
because
trying to
I'm
put a
seeing
new.
this Zoom screen, and you don't want that, right?
No, I don't want right now.
Well,
I want to
stop
start
sharing.
even from the
Stop
beginning.
sharing and start again is my suggestion.
Yes, yes,
So-
yes. Yes, you're right.
So as a side discussion, how many of us accept the existence of a possible existence of a magnetic monopole, or is it just a hypothetical for calculation purposes?
Yes, it will be exactly what I
Anybody
will
catch
talk
that?
about, guys, whenever I
Yeah,
will
well,
get it.
Cornelius,
I
binary
don't know how
mechanics
to
is
stop
one.
you. I don't know how to
You're
stop
just
you.
doing a poll to see what our opinions are at present, Cornelis.
Yes, 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 I will. Oh
Yeah, I'm
my
just
God.
basically asking how many accept the existence of a magnetic monopole.
Well, there is no evidence of it, so I'm not sure what the scientific community thinks about it. I think they think of it as a theoretical concept that's unproven.
Yeah, I work on the basis that it does not exist. But I mean, I'm open to looking at hypotheses, alternative hypotheses.
Yeah, like I said, I've always accepted that just any magnet is always just a circulating electron or charge in a motion. So if the circulating charge is standing still, it's a charge. If it's in motion, it's a electromagnet. But
In
That's the
binary
other one.
mechanics, the monopole, magnetic monopole, has the status of a postulate or axiom, and has produced very successful results. So it gets down to the question of what you want to assume. If you want to make it your postulate that only dipoles exist, magnetic dipoles, then that's an assumption, and you have to judge how far that gets you in terms of scientific advances with that assumption, as opposed to the assumption that there is a magnetic monopole.
Well, I think Dirac introduced the idea of magnetic monopole into physics, and that's not really been a very successful concept as far as I know.
Well, in binary mechanics, and I've made several presentations here in this same forum, it has been very successful. It's one of the basic postulates.
So what made you, Jim, in the first place, adopt it as a postulate? Did you just arbitrarily adopt it and you found it gave good results?
Well, yes. Well, with full quantization and following what the consequences of full quantization of length, uh, energy, and time, what are the consequences of that assumption or that postulate, or three postulates, if you want to call it that, that resulted in equations in which there are a magnetic field which is produced by these magnetic monopoles. And they're the L-type quanta in my presentations.
Well, there basically demonstrates the difference between quantum physics and classical physics, which I think is becoming is a big divide. Okay, you're back.
Absolutely right. You're absolutely right. I am back, guys. My crazy computer allowed me right now to come to you.
All right. So hopefully you have the presentation open in a
It's
window.
open. I checked already. Don't worry. I restart my computer. That's why it
All
took
right.
some time.
Yes, I
Share.
figured that. All right. And now
Share.
we're going. Oh,
Mm.
something. Okay, you didn't click on the right window apparently. You have to click
Share. I
on,
put share. Oh,
yeah, but you
no.
have to click on the window where your presentation is first.
I don't have this here respond that you allowed me to go. Okay, maybe let my months. What is going on? What is going on today? Return to meeting.
Well, if you close down, Vladimir, you'll have to ask Harry again to approve a request.
Yes, I asked him.
Oh, I didn't. I didn't. I didn't do. I didn't approve
Move
any.
my window. I know what I want to
It
load.
remembered. It remembered from last time.
Mm.
Yes, let me share because hopefully this. Can you see it?
There it is. There
Oh,
it is. Yeah.
yay!
Okay, thank you so much for your patience. I will try to follow my presentation with some comments. And then, as I told you, after that, we will talk about everything what you want to ask about magnetism.
Can we do full screen?
I have my full screen.
Make it
Do you-
bigger. There you go. There you go. Make it bigger.
Yes,
All right.
yes, I've done bigger.
All
You
right.
can even make it bigger. You're wasting a lot of space on the left and the right are just black.
On the right, you guys. On the left, there is nothing. That's why I don't know how to cut you.
Well,
Well,
if you
And
click
it's
on
enough.
the
I will read my
increase,
text.
Hold
Listen
on,
to
Ken.
me.
125%. You're at 125%. Go to 150 or 175.
What I can do with your pictures? Oh my goodness. Today I will not start my talk. I hope.
There you go.
150. But I cannot see you because your pictures. I don't need you. How to cut
right.
your pictures?
Okay, you have to move the pictures off to the side. Are they on the right or the left?
All right.
Okay, you should be all right. All right, we see it fine. Abstract. I can read it. There you
Okay.
go. All right, let's keep
Okay,
going.
okay. Can you read it? Good. At last, we fixed.
Well, okay, let's go. Tell me about
Let's go.
magnetism.
In electromagnetism, the term magnetic field refers to two distinct but closely related vector fields: magnetic flux density B and magnetic field intensity H. These fields differ in how they account for the medium and magnetization M. In a vacuum, they are related to the well-known equation B equals mu zero, it's a magnetic parameter, multiplied on H. In a magnetized material, this relation becomes B equals mu zero, H plus M. Within the framework of the world universe cosmology, the cosmic medium, comprising protons, electrons, photons, neutrinos, and universe-created particles, acts as a universal agent governing all physical processes and is inherently a magnetized medium. You see particles conceptualized as Dirac dipoles, formed by Dirac's magnetic monopoles possess a magnetic dipole moment proportional to the Bohr magneton. Any local concentration of Diracs within any material, including cosmic medium, induces both a magnetization field M and a magnetic field intensity H. This approach to magnetic fields within WC offers a framework for explaining a wide range of observed magnetic phenomena, including the dark magnetic field, the large-scale structure of the Milky Way's magnetic field, and other magnetic effects that are only partially correlated with objects observable in other spectral ranges. What does it mean? You can see magnetic fields without any objects. This is the main point about this dark magnetic field. Introduction. Maxwell equations form the foundation of classical electrodynamics. They were published by Maxwell in 1861. It's very important to pay attention to the years. He calculated the velocity of electromagnetic waves, not light, electromagnetic waves, from the value of the electrodynamic constant C measured by Weber and Conrad in 1857, 4 years before, and noticed that the calculated velocity was very close to the velocity of light measured by Fizeau in 1849, 12 years ago. This observation made him suggest that light is an electromagnetic phenomenon. He didn't put this stupid speed of light in vacuum. No, he put only electromagnetic waves. He saw the speed of them and he saw it's close. He told it might be electromagnetic phenomenon. That's it, what he told many years ago in 1861. The value of Maxwell equation is even greater considering Swain's result, showing that linearized general relativity admits a formulation in terms of gravitoelectric and gravitomagnetic fields that closely parallel the description of the electromagnetic field by Maxwell equations. Thiering pointed out this analogy in his 1918 paper immediately after general relativity. In his paper on the formal analogy between the basic electromagnetic equations and Einstein's gravity equations in first approximation. You see, what does it mean, general relativity, not general relativity? Einstein equations, it's a non-linear equations for Maxwell equations. Maxwell equations linear, and this is non-linear, that's it. For me, as an expert in non-linear objects, it's well known. If you have some very high intensity, you want to go from linear approach to some kind of non-linear approach. It is exactly Einstein's equations. That's why don't blame equations. They are good, but don't apply it for general relativity. It allows us to use formal analogies between electromagnetism and gravitoelectromagnetism, first proposed by Heaviside in 1893, before all this general relativity, before all of this quantum physics, everything. The world-universe cosmology is based on Maxwell equations. Let me give you a comment about Heaviside. It was genius physicist, genius. He wrote for us these Maxwell equations in contemporary picture of these equations. Before it was some nightmare. I don't know how Maxwell invented these equations based on very simple, experimental results of Faraday. And then only Heaviside gave us the equations, what we have right now and what I love it. My model is based on Maxwell equations. That's why I put so much attention to these equations, because this is the main basic theoretical basis for my model. Magnetism. Ancient people learned about magnetism from lodestones, naturally magnetized pieces of magnetite. A permanent magnet is an object made from a material that is magnetized and creates its own persistent magnetic field. In electromagnetism, the magnetic dipole moment is the combination of strength and orientation of a magnet or other object or system that exerts a magnetic field. The classical explanation, okay, let me first comment. You see, from ancient time, it's well-known effect. Let me ask you the question. This magnetite, they laid on surface of our Earth for hundreds and thousands years, and still they have a magnetic moment. How come? How come? What is the mechanism of it? First of all, how they were created? Nobody told about it. How they saved this magnetization during these thousands of years. How? I don't know. No explanation. The classical explanation, and you will see, of a magnetic moment has changed over time. Before the 1930s, textbooks explained the moment using hypothetical magnetic point charges. Since then, monopole Dirac's. Since then, most define it in terms of Amperian currents. I will talk about this later. In magnetic materials, the cause of the magnetic moment is the spin and orbital angular momentum states of the electrons, varying depending on whether atoms in one region are aligned with atoms in another. We believe that atoms, they have their spins directed in one direction to the North Pole of our Earth for thousands of years. And the same storm with orbital movement of electrons around nuclear and all of this momentum, they directed exactly to the North Pole of our Mother Earth for 1,000 years. How come? How they can propose quantum physics explanation with atoms, with spins, with orbital momentum for explaining these permanent magnets? Let's go, you will say they are not so stupid. Magnetic pole model. It's exactly a well-known model. An electrostatic analog for a magnetic moment consists of two opposing charges separated by a finite distance. The sources of magnetic moments in materials can be represented by poles in analogy to electrostatics, sometimes known as the Gilbert model. In this model, a small magnet is modeled by a pair of fictitious magnetic monopoles of equal magnitude but opposite polarity. Each pole is the source of magnetic force, which weakens with distance. Since magnetic poles always come in pairs, their forces partially cancel each other, while one pole pulls and the other repels. Can you see the poles? My Dirac, it's here, it's there. They use it right now. The magnetic force produced by a bar magnet at a given point in space depends on two factors: the strength P of its poles, magnetic pole strength, and the vector L separating them. The magnetic dipole moment M is related to the fictitious poles as M equals P multiplied L. It points in the direction from south to north pole. Okay. The analogy with electric dipoles should not be taken too far because magnetic dipoles are associated with angular momentum. In electrical dipole, there is no angular momentum, but there is angular momentum with a magnetic dipole. How come? How to explain it? That's why it's an analogy, but it's exactly wrong because there is no magnetic dipoles, magnetic monopoles, Dirac's monopole, and there is no magnetic field, magnetic moment. How come? The analogy, nevertheless, magnetic poles are very useful for magnetostatic calculations, particularly in applications to ferromagnetics. They're absolutely right. They're doing a great job. I mean, engineers, experimentalists, they use this model with some kind of dipole, but for them it's good, and they calculate their magnets perfectly because they're based on dipoles. They don't understand it that it's a dipole. They put, okay, we have some charges and some distance between them, and then they calculated everything what they wanted. Analysis of Maxwell equations. Maxwell equations vary with the unit system used. We will not rewrite well-known equations, but only provide the relationships between electromagnetic quantities used in Maxwell equations. Interested readers are encouraged to consult the reference article 8 for more details. It's paper 1980, 7 years ago. Table 1 gives the definitions of these quantities in C units. We stress that the electrodynamic constant C in Maxwell equations is defined as the ratio of the absolute electromagnetic unit of charge to the absolute electrostatic unit of charge, not as the speed of light in vacuum, as it is adopted now by contemporary physicists. Contemporary physicists. They know nothing about classical physics, but they're contemporary. Electromagnetism, I will pay attention to some definitions in here. Charge, it's Q. Impedance of electromagnetic field, it's Z0. What does it mean, impedance? It's so named wave resistance. We know it from physical textbooks. It's impedance or wave resistance. Then we were talking about electric current I. We will talk about magnetic constant, mu0. We will talk about magnetic field intensity, H, that it's measured with ampere over meter. Electric constant, I need to in some place. Electric field, I don't need. And of course, magnetic flux density, B, equals to Weber over meter squared. Let's continue. In Maxwell equations, there are two physical sources. The total electric charge rho E is small one, and the total electric current density JE. According to Maxwell equations, there are two measurable physical characteristics: energy density, rho E capital, and energy flux density, G E capital. Let me ask you the question. Even yesterday, we talked about the Maxwell equations, all this field theory for quantum physics, for atoms, for I don't know for what. Where we have in Maxwell equations this charge, there is no charge. Guys, there is only charge density, electric charge density, rho E. And current density, GE, it's a classical notion. It's, as you know, my attitude, it's ensembles of electrons of something. Right now, ensemble of electrons. We have only average charge density. Charge density. What kind of charge density we can put for electrons, for nuclear? What kind of charge density? How we can apply classical Maxwell equations to all these, quantum mechanics, quantum physics definitions. How? I don't know. Maybe you know. There are two auxiliary field quantities. It's very important. It doesn't exist. There are some tricks with mathematics. T that equals E epsilon 0, it's electrical parameter constant. E, it's electrical field, and P, it's a polarization, and R that equals B over mu0 minus M magnetization. The quantities P and M represent the macroscopically average electric dipole and magnetic dipole moment densities of the material medium in the presence of applied fields. It's exactly what I'm talking right now. I'm trying to put this D and H as a real field, magnetic fields, because they have a real participants of this theory about this phenomenon. Analysis of Maxwell equation, in which all quantities introduced above are arbitrary functions of space and time, has been done in literature. See, for example, these papers. It's only example. I found only a couple of these, papers, because it's so complicated theory. I will not put this theory on your shoulders. Even for me, it was very difficult to understand, believe me. But we are using our Maxwell equations in a totally different, way. In a vacuum way. There is nothing. There is no polarization. There is no magnetization. There is no medium. There is a vacuum. That's why for us, Maxwell equation, it's so simple. It's not as simple. We must upgrade this Maxwell equation with a real situation, with a real cosmic medium, with a real, densities of magnetization, of polarization. I will talk to you about this a little bit later. Very important comments about magnetic dipole fields made by Brown.
Okay, we got 4 minutes.
We'll finish and we'll continue. We have 3 sessions, remember? Let's finish this. His
Well, I don't
reference.
want you to get cut off in the middle when you're
No,
talking.
okay. No, I will not. 4 minutes will be enough for me to read all this because it's a very important point, because then I will start my own theory. There do, however, exist what appear to be magnetic dipoles, analogous to electric dipoles, consisting of adjacent positive and negative electric charges. It might seem as if the existence of magnetic dipoles is indirect proof of the existence of individual magnetic charges, assuming the only way to produce a dipole field is by just juxtaposing 2 oppositely charged magnetic monopoles. However, there is an alternative way of creating a magnetic dipole field without actually using magnetic charges. The alternative is an electric current loop. It can be shown that a circular loop of electric current produces a magnetic field that is, outside a spherical region enclosing the loop, nearly identical to the field of 2 adjacent and oppositely charged magnetic monopoles, if such things existed. We have 2 possible classical models for the source of magnetic dipole fields, one based on the juxtaposing position of 2 oppositely charged magnetic monopoles, and one based on a loop of electric current. These 2 models might be called Coulombic and Amperian dipoles, respectively. You see, you have the same magnetic field, dipole magnetic field, but the explanation might be through Amperian these currents, as it is done with atoms, with spins, with all this stuff, or as magnetic dipole based on 2 monopoles. It's exactly what I'm following right now. What I mean right now, everything is prepared for this magnetic dipole particle named by myself Dirac. You can see that most of the people, they thought, yes, if it exists. Unfortunately, they didn't find this Dirac monopole. That's why they stopped talking about some dipoles based on these Dirac monopoles. But I started to talk about this in 2013, 12 years ago, and I want to continue my next session with you based on some equation, and I will explain what is my output for my theory, for my understanding of magnetism as a phenomenon. I'm in time, sir.
Okay, we got 1 minute and 30 seconds.
Okay, if you have 1 minute,
Okay,
you want to ask about
quick
this,
questions?
main points, then I will continue and we will start with principal equations of electromagnetism. Not so many of them, but they're very critical and very simple. And it's very important for understanding what I'm talking about.
Okay. I don't.
Do you have any questions about this part? Don't talk about the next part, but about the history of magnetism. You're absolutely right. Ancient people, they knew about it. But first of all, let me ask you the question. How this lodestone were magnetized? The very good question. How? Nobody talking about. Where is the electromagnetism? Where is this electric field, magnetic field 1,000 years ago? It's very important to know that everything was done by the core of our Mother Earth. And they went up, out from this core, and they started to live on the surface of our Mother Earth due volcanoes, due earthquakes, and all this stuff. You see what I mean? That's why even magnetization was done inside of our Mother Earth. But then they moved with some flow, some particles.
All right, we're back, and I've started the recording again. So we need
again. I have this story, man. Why it disappeared? Why? It was downstairs, and now I cannot start it. Unbelievable. One sec, one sec. Let me do one more time. One more time. Computers, it is something, guys.
Did I approve
They
your?
behave as they want, not as I want, you want,
I know,
but
I
they
know,
want.
I know, I know.
I'm very sorry. Have your patience because, I left everything in place and now I open the next session. It disappeared. Good. It's good.
Okay,
I'm very sorry.
all right, start over again.
Yes, it's exactly what
Stop
I'm already
share,
doing.
stop share, and then send me the request. Then
It will be, oh my, how to stop sharing. Okay, let me
there's
open
a,
my paper, my article.
you have to go to the top bar, the bar at the top, where there's a red thing will show up and it says stop sharing.
Because I have it already on my screen, but I cannot share it with you. Or
Okay,
maybe
you
I
have
can.
to,
Okay, let's try. Let's try. Maybe I don't need to go up.
you
Maybe.
you need to click share screen at the bottom.
Yes, I know, I know. Let me start. Share. Can you see?
There
Yeah.
it is. All right, there we go.
Good, good. Let me put 150 that you will
Go to
see.
175.
No, I'm very sorry because I cannot cut you and don't touch this stupid crazy machine in front of me and you guys. No, 150 is so good
Okay,
scale that you can
so
read.
we reviewed classical physics and a couple of
Yes.
points.
And it's a history of classical physics about magnetism. Then I will start my
That
story.
was very brief. That was very brief. A
You
lot of
didn't
material
mention
there.
Ørsted's first detection of the magnetic effects of an electric current.
Yes, he
The
did
effect
mention
of
that.
magnetic effect, it was ancient Greeks. How can I
Yeah, I
tell
know,
you
but
what was the date?
no, in the 1830s, I think it was, working from electricity back to magnetism. Ørsted, the Danish Hans Ørsted, the Danish physicist.
Yes, 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 guys. What is important? History of physics. I don't know. So many genius people were in history, and all of them forgotten right now. Forgotten. We know something about classical physics. I'm so happy that I met them 300 years, 200 years, 100 years. I have so many names in my brains right now. Classical physicists, they were really great. They were genius. Nevertheless, contemporary physicists, they don't know anything about them. They know only their equations, and that's it. And they're so complicated that nobody can understand them. It's good. That's why, guys, history of magnetism, it should be some special book. By the way, Harry, you're the best writer for this point. That's why if you have your curiosity with magnetism, I will ask you to write the book about the history of magnetism up to now. And I will be more than happy to be the first reader of your book.
It's hard. It's at the GSJ, General Science Journal.
But it's not book. You have your history from ancient Greek.
It's in different chapters. There, each one of the papers, each chapter is a different file at the GSJ.
Okay. Guys, I will not. Many people, my friends, they recommended me to write a book, and I thought, no, it's too complicated for me. I will not
I
do it.
know.
It's
I ran into that too. So what is it? What's at the GSJ is a number of different chapters, and they're different files. It's not really one complete file, a book file. It's separate chapters are in different files. So you have to go to the General Science Journal, Harry Ricker, look for Harry Ricker, papers by Harry Ricker. And there's a whole bunch of papers there, or separate files, if you will, that discuss the history of magnetism up until the 19th century. I didn't really get much further than the 19th century. I was more interested in the ancient part. But you're right about a lot of the there's still a lot of stuff that's really not well understood, and I don't really think anybody really has a good model of what magnetism is, despite the fact that they're using quantum mechanics and I never really found that to be that convincing. This idea of magnetism is the spins of these valence electrons, and I'm not really sold on that idea, but yeah, I think this is interesting. So let's start up again.
Yes, let me give you the comment answering your, comment. You know what? I published already 39 papers. This paper I submitted to the same journal. It will be number 40. I touched these, Dirac particles for many other papers. I refer to them. And who cares? Nobody look into your references. This is the point. People now, they're so lazy. They don't want to do it. Even book to read, to write, it's a wasted time because in contemporary life, nobody wants to do it. That's why, let me remind you right now, the last two, at least two papers, I'm trying to do as short as possible. 3 pages, 4 pages, 5 pages, because I want you to listen to me, to discuss what I wrote in 4 pages in the paper, and then to explain you everything what I have in mind accordingly. This is the way how to go, sir. This is the main point right now for contemporary people. They're in a hurry. They don't want to read so long. They don't read books. They are going to artificial intelligence, and they will answer all the questions they want. That's it. Simple like this.
All right.
The age of the classical physics, by the way, finished in the 19th century. Quantum physics, general relativity, all these guys, they killed classical physics. They didn't know anything about classical physics. They invented so unbelievable physical phenomena like increase of each photon wavelength during his transfer from the star galaxy to us. It's unbelievable. It's so physical phenomenon that still I don't understand how each photon have his wavelengths and it's spreading during his performance in cosmos. Unbelievable. And everybody accepted it, and that's it. This is a way how to explain redshift. Okay, let's start. Principal equations of electromagnetism. First of all, I will start with Dirac quantization conditions, because he invented monopoles Dirac based on these equations. And he's a genius guy. He done great job. He gave us this, equation. I will use it in my theory, where QE is electric charge, Qm is magnetic charge, H is a Planck constant, and Z in this equation, I followed his this nomination, is a set of integers. It might be 1, 2, 3, whatever. The second very important and well-known phi-structure constant, alpha, that equals E squared, it's electric charge, electron charge, E squared, divided on 2 epsilon 0, it's electric constant, Hc. Well-known equation for alpha in electromagnetism. But there is no physics behind all this. It's some kind of parameter and so on and so on. In my model, let me remind you, alpha is a dimensionless Rydberg constant. Rydberg constant was measured in 1888, much before the quantum physics and general relativity, special relativity, and all this contemporary physics. That's why, alpha, they measured and they put in such an equation, because they used Maxwell equations, standard Maxwell equations, they played with it and so on, without knowing that alpha is going from Rydberg equation, from Rydberg constant. And that's it. You multiply on some A, the basic size unit, and you have your alpha immediately. You don't need any electromagnetic. Alpha is, from my point, alpha is so named universe constant. It's constant, provided us with this parameter alpha, and how we play with them, how we use it. It depends on our equations. In electromagnetism, right now, they use this equation. In my model, alpha is this the dimensionless Rydberg constant. Magneton. Can you believe Bohr magneton? This is the equation for Bohr magneton. It's E, the charge, H, Planck constant, 4 pi, mass of electron, and there is a very strong, very well-known value of this parameter. And you know why? Because this is a magnetic Bohr magneton was applied, was calculated based on a charge moving around nuclear, and there is a current with speed c, and there is a current with charge e, and the distance from 1 to 1 is so named classical electron radius. That's it. That's why its value of this magneton Bohr based on a classical physics. No, it's based on quantum physics calculations based on classical notions, space, time, and so on and so on. That's why, it's very important to say that even magneton Bohr magneton, they used right now in all the theoretical calculations, is based on quantum physics. They based on some very interesting iterations that electron moves with speed of light and so on and so on, because there is no choice. They didn't know how to define it, how to put some quantity, some equation for this magneton. Sorry for my emotions, because I cannot stop myself to see how much damage done by quantum physics to classical physics. This is my point. That's why I'm so excited, guys, because classical physics stopped by quantum physics, general relativity, and everything for 100 years. 100 years. They are dead right now because they don't know classical physics. Maxwell equations posit that there is electric charge, but no magnetic charge, monopole, in the world. Magnetic fields arise from moving electric charges and intrinsic magnetic moments associated with spin. This is the explanation of Bohr magneton for everything written in here. According to WC, the cosmic medium contains ordinary particles, protons, electrons with mass me and charge e, mass-varying neutrinos, and photons. Universe-created particles, including fermions UCF1, 2, 3, 4, many times I talked about it, with rest energy E0, 70 mega electron volt. It's a very important number. Magnetic dipoles formed by Dirac's monopole. Dirac's are the Coulombic magnetic dipoles, which represent the macroscopically average magnetic dipole moment density M. You see what I told? That M magnetization that measured in our classical experiments, it's an ensemble of Dirac's dipoles. This is exactly what I'm telling by this sentence. Elopes mass 2/3 of mass of electron represent electric dipoles of preons with charge 1/3 of E. Preons invented not by myself. There are some theoreticians, they talk about the preons as a part of the nucleus, of the quarks, of everything, with charge 1/3 of E. Why I took 2/3 of electron mass? Because two charges. That's why I took, it's my free parameter, 2/3. It doesn't matter for me what is the mass of it, but what is important, this is a dipole with charge 1/3 of E, invented by theoreticians in nuclear physics. They represent the macroscopically average electric dipole density P. You see what I meant one more time? There is ensemble of these dipoles, and this ensemble is responsible for average electric dipole density P. Always classical physics. The energy density in cosmic medium is about the proton energy density. Let me remind you, the proton energy density in cosmic medium, it is 4.8% of total energy density. That's why, in my view, and you know, each particle, I mean, even universe created particles, have the same energy density as proton. It means for me that all of them, Dirac's, Elop's, and all of them, they have what they have the same 4.8% of energy density. It's a lot. It's not something small. It's a lot, 4.8%. As I told you, even in our macro objects, stars, galaxies, and all this stuff, we have only 2.4% of baryonic matter, 2.4%. And all the rest we have in a cosmic medium around. And inside of this cosmic medium, over 90% of your energy density, you have each this particle have his own part, 4.8% in my model. The energy density in cosmic medium is about the proton energy density. Considering equation 1, I told you about this Dirac equation. QE equals to E, it's standard. Z equal 1, and using equation 2, because it helps me to transfer Q magnetic. Let me show you this equation. I can count this QM based on Z equal 1, QE equals E, and I need this number, epsilon, this number, yes, epsilon naught HC squared. And I use this epsilon 0 HC from this equation. I replace this part for alpha. You see what I've done? That's why it is a very simple transformation. But what is important? Immediately for magnetic charge, I have this very interesting question. It's E multiplied on C, it's electrodynamic constant, remember, divided on 2 alpha. And then I divided E over 2 alpha and named it mu, magnetic charge. Magnetic charge that is 67.5 of our electric charge. But what is very important in this equation? It is not simple E over 2 alpha. It is multiplied on a C, electrodynamic constant. Magnetic charge, it's not electric charge. It's analog of electric charge, but it's multiplied on C. It's a crucial moment to get then magnetic moment. Because how to get magnetic moment? You need your charge, you need your velocity, and you need some space, some dimension. I will multiply on A. And then you will have your magnetic charge. That's why magnetic moment of our dipoles, it is not rotation of some electric charge with speed c around something and so on. No. The definition of magnetic charge, it's multiplication of electric charge on this C, electrodynamic constant. And only then, when I will multiply on A, you will have your magnetic moment automatically. You don't need to rotate anything. You need only magnetic monopole composed of a magnetic dipole from magnetic monopoles. Nobody paid attention to Dirac's oh my goodness, monopole, equation. Nobody analyzed it. It was so simple to get this result. I showed you well-known two equations, and immediately I got this multiplication, charge over C, where E the elementary charge and mu, I named it mu, magnetic charge, equals to E over 2 alpha. It's 67.5 times bigger, larger than E. Then I calculated this Bohr magneton. You see, I showed it. I took the same equation, what is written here, the number 3, this equation, and instead of this combination, I put this definition of magnetic charge, and I showed what is a Bohr magneton. It is this magnet magnetic charge, mu c, multiplied on A, it's a basic size unit, divided on 2p. What does it mean? It's so named classical electron radius. It's exactly what I told you before. How to calculate this Bohr magneton? Take, please, your magnetic charge and multiply on classical electron radius, and you will have the same value. You see, it is simple. No rotation electron, no nucleus, nothing. You need only to multiply your existing magnetic charge over on a classical electron radius. It's a basic unit for quantum physics. In classical physics, basic units, it's a bigger, 2 pi times bigger. And A is a basic size unit. Many times I showed you this number. And what is important, it's not invented number. It's calculated number based on classical experiments in 19th century. In 19th century, before quantum physics, because all these general special relativities at all. That's why it is not invented. This basic unit is very important. There is a limit for classic physics. You cannot do less than this number. It's stop point. Then it's between classical physics and quantum physics. You want to talk about quantum physics? It's your business. Go with your business. If you're talking about classical physics, please stay with this minimum size of your units and forget about the less. I mean, this Planck, the constant Planck, the distance, Planck mass. Oh my goodness! All these Planck units, Planck time. It's all different for classical physics. It doesn't exist for classical physics. Thus, a magnetic dipole moment of Dirac equals mu c, as I told you, with a distance between magnetic charges equal to A, as I explained you right now, equals to mu c multiplied on A. For a concentration of Diracs, this is the number of quantity of Diracs in 1 cubic meter, you have magnetization M as very simple equation. You have the concentration of these Diracs and multiply on the units of the magnetic moment. They have already magnetic moment. You don't need to invent anything. You don't need to rotate anything. Only to take how many of them in each unit of volume and multiply on the value of each unit. Simple like this. Magnetization of the strongest neodymium magnets with the ferrum-ferrum distance approximately 0.25 nanometers is magnetization. It's a well-known number. It's the best magnetic, permanent magnetics in the world. They were so named neodymium, ferrum, Bohr magnets. They invented by Chinese. They produce so many pieces of magnets, and all the world right now use only their magnets because they are smallest, they are strongest, and and they're so cheapest. I checked even on Amazon. You can buy pack of them for $10-20 only. That's why it's a well-known business right now. Very good production of them. You don't need to invent any new magnets because you have so unique, so good. That's why now there is a fight in the world for so-named rare earth elements, because neodymium Bohr is a rare element. That's why you have to get them to have your magnetics. Simple like this. The calculated value of Dirac's concentration, I calculated, you see, I have the value of M, I have my value of M Dirac, mu Dirac, then I can calculate the concentration. It's a huge concentration, to 10 to the power 28 units per cubic meter. It's huge. It's, as I told you, at close to atomic distances between ferrum, between some other, components, it's a little bit more, about 1 nanometer, and so on and so on. But what I calculated 0.39 nanometers. You see, small, very small number. It's close enough to the minimum distance between ferrum elements of this composition. It's alloy. It's alloy. It's not composition. It's alloy. And who invented? Chinese guys. In classical electromagnetism, polarization P is a macroscopically average electric dipole density. In WC elopes as electric dipoles d elope of preons with charge 1/3 of E, and separation A, I took the same separation because I don't have a choice. This is a minimum, I can use it. With concentration N elope give the same equation. P equals concentration of elope multiplied on electric dipole of elopes. It is not dipole this dipole magnet, oh my son, I'm so sorry, magnet between magnetic charges and its dipole moment. And here mu c is a dipole moment. In electric, it's only dipole. There is no moment because there is no c. It's not multiplied E, the charge of electron not multiplied on C. It is simple E. That's why analogy is, but the values, the meaning, the so-named electrical charge, it's electron, and magnetic dipoles, it's Dirac's. They have totally different value and even different, physical meaning. We emphasize that H and D are not merely auxiliary quantities, but represent real field components. Why real? Because I give you real performance of these, Dirac's and elopes in my model. There was no these particles. There was something, some mathematical, some equations, some way to how to work with them. But I saturated these equations with the players of this, electromagnetism. What is important? What is important? Very important, by the way. Let me tell you right now. We have our magnetic dipoles. The very good example I told you, magnetic needle of compass. You can put your electric wire, you can put these, electric dipoles around and to go with current, charge current, and you will see that and put a lot of ensemble of these, magnets, needles, this, oh my goodness, compass, and see that all of them will lay around the wire and they will follow these so-named magnetic lines. Faraday invented this definition, magnetic lines. Then you can see that magnetic field around the electrical charge is around electrical charge current. That's why you have the circles of these compass compass needles around this wire. But what is important, you have the same compass and you can follow your magnetic field of the Earth. If you will put ensemble of these magnetic needles, and all of them will look to the North Pole. Why? Because magnetic fields line is going to poles. And if you will combine all these needles together, you will have exactly what I'm talking about, ensemble of Dirac's. My Dirac's is a tiny needles of your compass. But what is important? Magnetic dipoles, they follow not only magnetic fields, they are following electric fields too. That's why it was a very right definition of this magnetic field composed by electric currents. It's correct. But what is important? Electric current they follow these electric current magnetic fields, but magnetic fields is with Earth, and you can follow magnetic lines of the Earth too. They're responsible for magnetic field and for electric field too. You see, it's very important to show that they're responsible for both phenomena. Dirac's, I mean. Multiplied Maxwell equations. Most articles solve Maxwell equation using steady-state solutions. Steady-state solution without anything for vacuum. And we're doing all these conclusions, well, all these theories based on a steady-state Maxwell equation. Why? Because it's a simple solution, mathematics. Who is the ruler of all the physics right now? Mathematics. If it's so complicated to solve the nonlinear equations, immediately cut them, all these members of your equations, the pollution, cut them, and start to talk about something in a very simple equations. You see, simplicity of equations manage our physics. It killed our ether or my cosmic medium. It killed everything because we are talking about Maxwell equations in vacuum only. That's why we invented this c as a speed of light. I don't know still what does it mean. But what is important, we invented even this redshift explanation as a wavelength spreading during performance. Why? Because there is no other choice. There is nothing in vacuum. How to explain this Z without a medium? And this is our contemporary physics. Guys, I'm very sorry. Cosmic magnetism. Beck and Wilhelmsky discuss the omnipresence of cosmic magnetism. Most of the visible matter in the universe is ionized, so that the cosmic magnetic fields are quite easy to generate and due to the lack of magnetic monopoles, hard to destroy. Magnetic fields have been measured in or around practically all celestial objects: the Earth, the Sun, solar planets, stars, pulsars, the Milky Way, nearby galaxies, more distant radio galaxies, quasars, and even intergalactic space in clusters of galaxies have significant magnetic fields, and even larger volumes of the universe may be permitted by dark magnetic fields. What does it mean, dark magnetic fields? You have magnetic field and you don't have anything around. How to explain these magnetic fields without anything? Why I started this paper? Let me tell you what was the key of my intention to write this paper and to talk to you. I wrote this paper, some small short papers. I saw some video about Voyager spacecraft, and they have so many magnetometer beyond the heliosphere. And with this Voyager, they observed magnetic field intermittency. Can you believe? After heliosphere, contemporary physicists expected what they expected, that it will be smooth flight because they left our solar system. It is some kind of vacuum already. It should be some quiet performance of this Voyager outside of the heliosphere. On the contrary, this Voyager measured some storm of magnetic field. It's going up and down, back and forth, and so on and so on. What is important? They invented even some human beings, not human beings, some entities in the cosmos. They arrange this magnetic field around our solar system. When I read this, bullshit, I couldn't take it. I thought, okay, it's time already to tell guys, don't invent these bullshits about somebody else who is more powerful than us. They can even arrange our magnetic field around our solar system. It was already overhead for me. I was overloaded with all this stupidity. That's why I told myself, let's write down about Dirac. Let's explain all these facts, what we have right now. Everybody knows about it, but there is no explanation at all. Sorry for my emotions as usual, because I'm classical physicist and I don't like all this contemporary physics. They killed classical physics. They killed it 100 years ago. WC explains field and gas. Oh my goodness, sorry for my emotions. WC explains field and gas flow patterns similarities. They observed in paper number 17, you can see the details, as Dirac flows along with diffuse ionized gas. As I told you, it's responsible to electric and magnetic fields, no problem. The Milky Way's magnetic field structure, dark magnetic fields, and other related phenomena can be explained through Dirac's dynamics. You have your concentration of Dirac dynamics. You have your magnetic field. You have your flow of this, ensemble of Dirac. You have your Dirac's magnetic currents. You see, it's dynamic of Dirac particles only. Like electrical particles, we have charge density, we have current of electric charge. The same story with these dipoles, Diracs. You have your energy, the density of them, you have your magnetic field, you have your moving, you have your current of these magnetic dipoles. Proof offers answers to cosmic magnetic field origins, such as their appearance in young galaxies and intergalactic fields. You see, you have your young galaxies, there is nothing, and nevertheless, you have your magnetic field. That's why, and why? Because magnetic fields depends on Diracs, and Diracs, they are coming from the eternal universe, from the very beginning. And all the time we have 4.8% of energy density in conjunction with Diracs. That's why it is not the beginning of Diracs, 2 billion years, 13 billion years. From the very beginning, 14.226 billion years ago. You have Diracs. They saturated our world, universe, eternal universe, saturated our medium, our world with these Diracs from the very beginning. Then they can start playing from the very beginning. That's why you don't have even galaxies, but you have already your magnetic field because you have Diracs, and they have some play of these Diracs, as I told you. You have the concentration of them, you have your currents of them, and immediately you have a magnetic field. So, I'm sorry for emotions as usually because I'm overloaded, especially with these Voyager explanations. No, I cannot take it. I cannot, guys. I don't believe in any gods except eternal universe. Maybe you name it God because it's our creator of all our matter. But all the other gods around us, forget about them. I don't like it at all. I'm so sorry. Conclusion. Universe-created particles, Dirac, are responsible for magnetism. This is my main conclusion. Dark magnetic fields and interstellar magnetic environments confirm Dirac existence. You see, if there is no Diracs, there is no any explanation. You must have something. How to explain? And for me, if you will accept my Diracs, then they exist. Dark matter, they name dark magnetic fields, they're composed of universe created particles, Dirac. We should develop a comprehensive theory of intergalactic electromagnetic signal propagation considering WC cosmic medium. What I mean by this? We are trying to solve our cosmological problems mostly with our equations. Stop doing equations. Use nonlinear equations of Maxwell equations. Put inside of them all the parameters I talked about, and go to your computers, so good computers. Go to your artificial intelligence and ask them to solve your equations for the chosen parameters of your theory, of your model. Okay, let's have this density, let's have these currents, and so on and so on. You see what I mean? That's why we must use our contemporary possibilities to solve this non-linear equation instead of talking about linear equation with all the bullshits what we have right now in our classical physics. WC can serve as a fundamental basis for cosmic magnetism. I'm not talking about, I explained everything. No, it's only basis as all my model. My cosmic medium, all what I've done for 24 years, guys, it's only basis. And new classical physics should be developed, must be developed by all physical communities. That's why I invited even astronomers and astrophysicists. Please.
Recording. Go ahead with your request.
Because I'm practically.
I have to apologize. Something went wrong here, and my clock wasn't giving the right time.
You see, it's a contemporary.
I would have warned you that it was going to cut off, but my clock somehow or another didn't indicate that the time was up.
I felt it, and I closed by point. Done. All
right.
That's why, let's continue discussions, guys. Yes.
Yes, okay. Okay, very interesting. I'm not sure what to. So, are you finished with your presentation?
Practically, yes. Let me tell if I can open it. If we don't need, it's okay. But what is important? It was my acknowledgments. Let me tell you, I must name the guys. They've done so much in my life. It's my teachers, great teachers, Prokhorov and Manenkov. It's a genius, Dirac and Tesla, and the last one, but the best one, Harry Ricker, who helped me to modify, to clarify my model by asking very good questions May the last year. I will never forget your input at that time. I was in my vacation in Nevada at that time, and you started to ask me these very good questions. What does it mean? Why you named the dark matters and all this stuff? You were absolutely right. Only because of you right now, I have some clarity in my model. Thank you very much, sir.
All right. Well, I appreciate your saying that.
That's what I wanted to finish.
Okay, I found this very interesting. I'm not sure what other people's comments are, so I'm not sure what we want to do here. Does anybody have any questions?
Yes, I'm ready to answer questions, guys.
And
Well,
we have
let's
no
talk about
questions.
yesterday meeting. If we don't have any questions, it means I succeeded, guys. I tried to be as simple as possible, and I tried to explain you with my comments much more than I wrote, because it was like a summary what I wanted to talk with you about. That's why, But if you don't have some questions, I achieved my goal, guys. I explained you in a simple way. What does it mean, this new approach to magnetism, to theory of magnetism, to saturate this in existent? No, it's not existent. It's auxiliary magnetic fields and all electric fields. That's why I saturate it with the real but universe created particles. By the way, it's a very important. These Dirac particles, we have a lot of experimental results, observations in astronomy with gamma radiation around 70 mega electron volts. And there is so simple explanation for some unique elementary particle, how it was created, how they've done it. There is no any explanation. And why? Because there is no way for them to explain this 70 mega electron volt from galaxies, from dead galaxies, from all around. There are some results. In my papers, I put a lot of references on them and so on and so on. And nevertheless, 70 mega electron volts, they suppose that it's our standard particle. No, it is Dirac's. That's why I have, by the way, I put these references 12 years ago in my first paper. That's why I started to talk about them 12 years ago, but only now Voyager killed me. Okay, guys, let's finish this business, because to invent these new gods around us, I don't want it. I want to be a human being. I want to be unique. I want to explain what I can see right now by ourselves. Forget about them. This is exactly what my intention to give you this paper and my presentation.
So in a nutshell,
One sec. I did finish. I'm so sorry. And the other one, why we need this dipole Diracs? Because Dirac told that if we have a monopole Dirac, we have this quantized electrical charge. You see the value of Diracs. It's not only what I told right now. It's quantization of electric charge E because of Dirac dipoles. It's not because of monopole, as Dirac supposed. It is because of Dirac dipoles. You see the value of this particle I named behind this genius guy, Dirac, because it plays 3 different games in my model.
So in your model then, I should let James go first. I think he was trying to speak there.
Okay, so James, I'm very sorry I didn't finish. That's why I stopped you. Please ask your questions. Usually you have very good questions.
well, that's okay, Vlad. Don't worry. So in a nutshell, the Dirac is a kind of particle, and that is responsible for magnetic effects that we measure. Would that be a correct statement?
Yes.
Okay. What is basically the defense or rationale for defining a whole set of different particles, universe creating particles and others, bosons and so forth, based upon EM wavelength or EM energy that you do? Like you have a table that, this particle is associated with so much electron volts, and another particle is different electron volts, and so there must be a different particle. Is that a fair statement of the logic?
Yes, logic is fair, but well, let me tell you the two questions in principle you gave. The logic is fair. What does it mean? All the particles, they have a very simple equations. For all of them, for rest energy, it is E0, energy 70 mega electron volts, multiplied on alpha in a different power. All of them different in alpha. Why alpha? Because if it is universe created particles, you can use only some constant. Particles must be constant. There is no variation. The eternal universe, they created some particles and it knows nothing about our world, about what is going on after that. You see what I mean? Eternal universe can generate particles, and this is the main point of my model. All continuously generating of particles. They must be constant rest energies. Universe cannot create with variable the energy, rest energy of these particles. That's why alpha in different powers. This is the logic, and all of them, alpha is from power -2 to power alpha in power 6 or 5. I don't remember exactly. 6, it
Well,
seems to me.
that's an amazing assertion, and perhaps you could focus on that in a future time in these sessions. How you really got to that assertion. That's an amazing assertion to make. And thank you for
Yes,
your response.
thank you so much. But what is important, even in my first paper, 2013, I put all these numbers, 70 mega electron volts, 3.7 kilo electron volts, and all this stuff. And immediately I found the confirmation of their existence by gamma radiations. We have so much coming to our Earth from the cosmos. And I found these lines in cosmos, in galaxies, in all these objects around. Immediately I found. That's why experiment. By the way, the main point.
So these are absorption lines? These are absorption lines?
Gamma lines. You have your gamma spectrometer, and you can see these lines by gamma spectrometer on our satellite, something like this, or even at motherland.
So the spectrometry gave you the list of electron volt values that you use.
It's against the experimental approach. On the contrary, I've done differently. I invented this table of particles, and I told you what was the meaning of it, how I came to it. And then I look for experimental observations, confirm my particles. I invented, first of all, particles, and then I saw experimental confirmation. But what is important? Let me tell you two very important points. The first point, alpha. There is so-named basic unit of energy, 70 mega electron volts, E0. It's Hc over 8. Everybody knows this formula, 70 mega electron volts. But what is important, mass of electron is alpha multiplied on this M0. How come? Alpha managed the mass of electron from the beginning. The second very important point, Rydberg constant. In 1888, Rydberg, he measured his spectrum of sound, they found some lines, and they put some formula, his formula. But in this formula, in contemporary language, there is alpha in cube. Can you believe it? Two very important experimental results, they have already alpha. Mass of electron and Rydberg constant, they have this alpha. That's why it was some main point for me. How can I start? Why alpha? Because I have at least two classical witnesses, mass of electron and Rydberg constant, they depend on alpha. Can you believe it?
Thank you. I just have a quick suggestion before others comment, because I don't want to monopolize the comments here. My suggestion is that maybe in a future presentation, rather than trying to cover the big picture as you usually try to do, I think, you really focused on a very small part of it, like where you got these electron volt values and what the thinking is and the powers of alpha and so forth. And in other words, just a little part of it. Devote the whole session to that so we can really focus in on what you're exactly saying. Thank you.
Okay, thank you so much. Many times I demonstrated this table of particles, many times, practically in all of them. That's why you can find short explanation in any particle right now.
Right.
But maybe I need to
what
go
I'm
with
fishing
details.
for is a whole presentation just on that table.
Okay. Let me ask you the question.
The thinking behind that.
Yes. Let me ask you the question.
It's resulted in some rather remarkable assertions. And rather than trying to give the big picture, in almost all of your presentation, you cover maybe a dozen different topics, you might say. I just as suggesting for your own benefit, we could probably play the game with you a little better if we just focused on one little thing and really drill down on that particular table and how the values are and what they mean and so forth. Thank you. Let others comment. I don't want to talk too much here.
Thank you very much for a very good suggestion. I started to follow your suggestion by the last sessions. The previous one, cosmogony, it was 3 pages paper, and we talked about cosmogony, the beginning of the world, the beginning of cosmos, of universe, whatever. It seems to me that I started already. Today, I talked about one only magnetism phenomenon. Maybe I achieved already this goal with you guys, then it's the way to go. That's why I started a little bit earlier than you suggested. Two papers, the last one, and 2 performances, presentations, we done already in this way. But do you know, I want to develop in my mind, of course, the whole building of classical physics, new classical physics. Can I do it in my real life to talk about all of them one by one, even each week? I don't believe that it will be enough time for me to share with you all these basic ideas. That's why, I'm trying. I done this cosmogony. It was the very first one. I talked about it. Right now, I'm talking about this magnetism because I mentioned it. I told something about it, but today it was particular on this phenomenon only. But do you know how many phenomena we have in our classical physics? I don't know. That's why all the time, by the way, thanks to Harry, he put this sentence in our mutual paper. It is written, we invite with him all the community, all the physical community to take part in developing of this new theory, guys, to take any part of it, any small issue, and start everything from the beginning. We cannot replace with Harry all the physical community, guys. I invite you, if you have interest in any of the classical physics phenomena and you wanted to consult me, I am ready to consult you, and please do your job as a physicist.
Okay. Yeah, we need some 20-year-olds here in our group. 20-year-old physicists.
Yeah, right. Well, I think we just have you have an overwhelming amount of information and an overwhelming amount of I mean sidetracks. By the time you get done talking, I don't even remember what you started with anymore. And then when someone asks a question, it's another 10-minute answer and half of it doesn't relate to what's being said. So I felt like after the first 15, 20 minutes, we could have taken a break and answered and asked questions rather than try to go on and on because your main point was made in a short period of time, possibly, but it just it was overwhelming. So I can't say that you really reduced it like you claimed to be, but I did write some things down to try to have some reasonable questions because I realize that when you talk, by the time you get to the end, it's well, it's not to baffle them with bullshit thing, but it's just baffle them with overwhelming amount of different thoughts is what it is to me. And so by the time I'm done, I'm done. I'm just totally disorganized. So that being said, like I said, I did write some things down. You say partly was you work with this classical physics, but I'm not quite sure what you mean. You're saying you're doing a classical physics, but I'm not sure what you mean when it doesn't seem like it coincides with, I mean, all these extra particles you have. That doesn't seem like classical physics. The idea that you can have a magnet without an electron, a moving electron, doesn't seem very classical. And you have a situation like you say, well, the electron is derived from the Dirac particle, which is a magnetic particle. So you're reversing things. It sounds like where you're saying a magnetic particle actually creates an electric field. Is that an electric particle?
Magnetic field? No, not electric. No. The last, everything what you told before is correct, but at last comment, not correct. Let me tell you, very important. First of all, it turned out that in our talk today, we had 3 sessions. Now this is number 3. The first session was only about the history of this phenomenon. That's it. It turned out that the first 40 minutes was only history. I started my second session with my model theory, and I finished exactly during the second session. You see, only 40 minutes I put on my 2 pages paper, because it was 2 pages only, and with all my comments, I tried to explain each paragraph, each sentence with my emotions. What does it mean? That's why, for me, I tried to do today my best to show you only one phenomenon. Only one phenomenon only. That's it. Simple as it. And you're absolutely right. It's my drawback in all my presentations with Ian. I've done 10 different presentations, at least 10 presentations I done with Harry, and always I have these feelings that I am giving you too much in each of them. That's why the last 2 presentations, it was exactly trying to tell about something small, smaller than today. I cannot do it, man. Without these 3 equations and about the each sentence explained, I cannot give my conclusion based on this, very simple, well-known equations. That's why thank you so much for good proposal as usual. But I'm so sorry. I'm trying to do it. But there is such a saying, by the way. Oh my God! It seems to me that it was Napoleon who told about the letter. He sent his letter to his friend, and it was an excuse. Sorry, I wrote to you very long letter because to write short letter, I didn't have enough time. It's exactly what I'm trying to do right now. I am trying to write very short presentations, and it takes some time. Believe me, it's very difficult to do. And even this, too much for you. I don't know what to do, guys.
Well, okay. I have a question. You speak of there is no rotation in required for the magnetic field. that what's required. So you do agree that what's required is a moving electric charge to create magnetic field. Then that is understood.
Yes. I am not stopping electric current. Yes, electric current in wire, and immediately you have your magnetic field inside of this loop or around this electric current. Electric current can create magnetic field. Yes. No,
Okay.
I am putting additional something, not cutting something. No.
Okay. But you're also saying that there's no rotation involved in no angular momentum in the electrons. You made that comment, I believe.
Let me tell you my understanding. I have no idea about quantum physics. I don't know what they're talking about. Spin, orbital rotation, all these fields they invented. Let's talk about the yesterday.
Okay. A more simple
That's why
question
I
then.
don't know. If you know what does it mean, speed or orbital angular momentum, please report about it and convince me that it exists.
Okay, so basically, if an electron is moving, you get a magnetic field, but if it's static, you don't get a magnetic field. Is that's classical physics?
Classical
That's
physics, when you
neutral
have your
interpretation.
ensemble of electrons, each electron, it's not classical physics, it's a quantum physics. This is exactly my point. I told each time I'm talking about the same. If you quantum physics, go with single object. If you have your classical physics, it's ensemble of them. That's why no, electrons doesn't move in my mind. Some density, charge density, ensemble of electrons, they're moving inside of fire, whatever it's
Okay.
doing.
But then there's some kind of method within your model then that somehow converts that mechanical motion or that linear motion of the electron pattern to a magnetic field. So a static group of electrons, if you will, or a statically charged atom in motion will create a magnetic field, but one standing still does not.
I don't know what does it mean, standing, charge,
Well, it's
nuclear.
relative.
I don't know what does it mean, guys. All these, definitions, I don't know them. I'm very sorry. Let me tell you my understanding.
Uh-oh.
Yeah, it froze out.
Gas around us. We know the gas consists of molecules of oxygen, nitrogen, hydrogen, whatever. Can you hear me? Because unstable movement.
Yeah, I can hear you now again.
Yes, okay. And then we have this ensemble. Do we know something from classical point of view? Know something about molecule of oxygen, molecule of nitrogen? We don't. But we know that there are some particles. And ensemble of these particles, they're moving. All of them, they have a different energy, kinetic energy, all of them. Yeah. Average kinetic energy is a temperature. Temperature knows nothing about these components, about these molecules. But molecules know nothing about the temperature. You see the border between quantum physics and classical physics. That's why I don't know anything about spin, nuclear, quantum physics. I don't know from classical point of view.
So you don't go down
molecules in our gas. I don't know what they are. I don't know. I know they exist. They have kinetic energy. Then I'm doing some averaging, and I found the temperature. Average kinetic energy of these molecules, it's my temperature, classical notion.
Okay, so you don't really go down to even the electron cloud concept of the atom or anything like that.
No, I'm not. I'm classical.
Just,
and by the way, let me tell you, we have a loop of electrical current, and we have inside of this loop, we have with you magnetic field. But loop, it's a classical, big one, big classical. You cannot move this loop of your current to the atom. How come? This is my main point. The transfer of all our classical physics, mechanism, equations, all this stuff, to the basis, to the quantum physics, it's absolutely wrong. In quantum physics, there is no electromagnetic field, there is no magnetic field, there is nothing. It's a classical notions. I'm
Well, I
trying
think
to
that's wrong. I
convince
think
you
that's
with this
overstatement
many,
about.
many times.
I think that's an oversimplification of quantum physics by far, because there are many different fields in quantum physics, and the particles are derived as patterns, as perturbations and disturbances in those fields, and that's how they define particles. So I would say that that's way oversimplification of
You are wrong.
actually
I'm sorry.
the quantum mechanics, quantum electronics go down to define how a particle is made and what it actually has to do in order to get the property it has. So it's much more detailed than you give it. So I think that's part of it. But anyway, you mentioned Bill Lucas at one point, and his he does go down into the atom and stuff, and he does speak about why atoms and molecules arrange themselves the way they do, because of the magnetic arrangement within them, and he has electrons within stable orbits, but not necessarily around the center of the nucleus, but off onto the side to explain that. And so he has an electric charge that is rotating in his. So anyway, yeah, I see you shaking your head no. So, but you ask how does these magnetic fields persist for eons and for years and that? And you have to ask the same question: how is it that an electron continue to orbit around a nucleus infinitely? But since you don't go that deep, it's insignificant to your theory.
Let me tell you, first of all, you talked about that we look for particles in cosmos and so on and so on. Let me remind you that our instruments, they're classical instruments. You cannot see each particle. I'm very sorry, man. That's why your first sentence that we can see these particles in cosmos, wrong. We cannot see them. We cannot, because we are classical objects. Our instrument, it's a classical object. We can see only classical phenomena. We can see only ensembles of them. The second very important point, in quantum physics, you can do whatever you want. I don't want to talk even about, because for me, many times I told, even these definitions, space, time, gravitation, they arise only when they have cosmic medium. All the classical physics equations, phenomena, all depends on a cosmic medium only. There is no cosmic medium, there is nothing. That's why in quantum physics, I don't know what kind of equation. If you have your rotation, please give me what does it mean speed, what does it mean mass, what is it, the distance, and so on and so on. They don't exist. These notions exist only in classical physics. That's why it seems for me, that quantum physics might be only mathematical, only. That's it, without any
Let's not go
some
too far into.
particular
Let's
classical
not go too far
notions
into.
transferred to quantum physics.
Let's not go too far into classical physics, into quantum physics. We can go down as far as even chemistry and have to explain how the chemical bonding in that occurs. And that even goes into the arrangement of atoms, the arrangement of charges within the atoms and that, in order for chemistry to work. So chemists aren't quantum physicists, but chemists do deal with the structure of atoms to a degree. And it's a model. Yes, you can't see
Model,
a dot that's an electron.
yes.
Just like yours is a model.
Yes.
Right, 100% model. So they basically work on a different level, giving a model that explains these things too. But it explains it down to a lower level than you do. Instead of going to that lower level, you just say, well, there's a magnet, so there's a magnetic particle. But in actuality, there isn't a magnetic particle. There's an electron that's moving that creates the magnet at all times. If there's a magnetic field, or if there's any magnetics emanating from a point, it's because of a moving electron.
Okay, we got 10 minutes.
Okay, let's stop it, because I have no other comments. I told you already. That's why We are classical objects. We are looking for classical notions, classical physics, and that's it. That's it. Simple as it. In quantum physics, how we arrange molecules,
let's not get into quantum physics because, like you said, quantum physics is
chemistry, it's
fuzzy
already
to
a
a lot of us.
result of quantum physics.
Let's
It's a
go to
result.
chemistry. Yeah,
Two atoms
even,
to bond. It's a quantum physics. How you bond two atoms. I don't know. Maybe you know. I don't.
but the chemists do because they've made many things. Anyway, Harry,
Oh,
I'll
yeah,
let you
yeah,
take
I know.
over here because we're
I know.
10 minutes, like
Okay,
you
thank you
said.
so much. Maybe
Just
somebody
one very
else can
brief
ask.
question, if I may. I don't know if I totally understood your problem with the Voyager explanation. Was it about the variation of the magnetic fields or something? You seem to have a major problem.
Variation, yes.
Yeah. So
Uh-oh.
you don't has he gone again?
Huge variations.
You
It's
didn't
what
accept their did you not accept their statement of the variation or their explanation of it?
statement. It's experimental result. They have magnetometer and it measures these signals. They don't have an explanation for it, as usual. Answering the previous question, I'm sorry that we have not so much time. Let me tell you that model how to have two atoms together. It's some model. My model, it's based on experimental observations of gamma rays, of all what we're talking about right now. There is a difference. My model, it's experimental model. All of these conclusions, I have your experimental classical results confirming them. Sorry for interrupting you because I didn't want to finish. I wanted to finish with Cornelis. Please continue. I'm very sorry that I interrupted you.
Actually,
So
it's an
experiment was
observational
correct,
model.
everything
It's
is
not
fine, but
experimental.
explanation wrong. I'm sorry?
Well, the data that you're really talking about are observational data. In science, we have experimental data, which means a controlled experiment with independent and dependent variables. And none of really the data that you've talked about falls in that category. It's all observational data, so that you might just want to substitute the word observational for experimental in your talks in the future to be more accurate.
Yes, you're absolutely right. But to explain all these objects, sun, earth, galaxies, and all this stuff, one guy for me, it's impossible. My intention is to put some attention that you can start talking about your particular phenomenon based on a new theory developed by myself. That's it. It's impossible. Impossible. Astronomers, they've done so much job, so good job, observation so unique, and there is no explanation at all. I'm asking them, please take my model as a basis only, and try to explain your observations, the experimental results, based on my model. That's it, what my intention to all the physical community.
Yeah, I can't even begin to explain my model based on your model. So there's no correlation whatsoever.
Your classical model, what is your classical model? What
All
is
right,
about?
all right.
Okay.
Does anybody else have any comments or questions? We got 5 minutes. Okay. Anybody have any suggestions for a talk next week? Anybody want to volunteer? Don't have many volunteers. Well, I guess I'll have to come up with more talk on special relativity, I suppose, which I guess we've heard enough of. Roger, I understand, is going to talk about, he's going to criticize quantum mechanics in his upcoming Saturday morning because apparently people are tired of hearing about special relativity.
Yeah, it's good move, Roger. It's very good. Cornelis, why you cannot give your talk? You told right now this, I have my model and I cannot use your approach and so on. Please talk about your model.
I won't make any promises but I'll try to contact Harry if it's possible. I will be on a trip trying to take care of my sister-in-law that's having surgery. So I'm not sure where I will be next Sunday. But if I know I'm going to be someplace that I can communicate, I'll let Harry know that I can maybe give a talk.
All right. Well,
All of you, let's help Harry.
I'm prepared to talk about special relativity, or we could talk about.
I think I can speak maybe to charge and moving charges and their relationship to the structure of an electron.
All right. All right. We got 3 minutes.
Let's talk about the yesterday talk about the collapse, general relativity, special relativity. You know, when you put your classical notions, fields, electromagnetic, this and this, to some electron, photon, something, from quantum physics, it's absolutely wrong. He used all these questions from classical physics, and I couldn't take them. This is the first point. He took these electromagnetic equations of Maxwell and they put in his model, in his theory. I cannot accept it. I didn't want to tell yesterday about the difference between quantum physics and classical physics, and I promised you to talk today about this issue. That's why special relativity, general relativity, this is classical physics. They are classical physics only. Please stay with classical physics only. When you start to talk about something classical in words of quantum physics, I cannot take it. I'm so sorry.
I don't think they're any near classical physics, but that's okay. Go ahead, Harry.
My comment was one of the things that struck me is he showed those equations of the transformations of the electric and magnetic fields, and they show up in all the textbooks. And my comment is, I have no idea what they mean. I have no idea how to use them or how to interpret them, and so they just show up in all the books and they go, here's the equations that we derived from special relativity using 4 vectors and Minkowski space-time, and here they are. And I go like, fine, what do they mean? It's just, I don't understand any of that stuff.
He named collapse, special relativity and general relativity. How did you understand what does it mean collapse? He claimed collapse. What does it mean?
I think he's just meaning I think he just meant he's saying it fails. It's not provable.
Right. That's
my own view is that he's not the only one who has spent a considerable amount of time developing a theory based on classical concept, which I applaud as yours, Vladimir. But I think there's a fixation on trying to replicate the results of modern experiments which claim to validate special relativity. So, for example, take the excess precession of the perihelion of Mercury. I don't know if you got, I put in a point there, but I think they're making a big meal about that. It's a very, very small amount, and it's probably due to observation error. And this 43 seconds was a magic figure, which was around in 1915. And Einstein said, look, I've derived it, and so on. Gerber said, some people say it's 59, it should be 59 seconds, and so on. So, these are very, very precise values. I'm impressed, actually, by a lot of his work on classical physics, but I think he's got too much of a concentration on trying to replicate the results of relativity.
All right, we're coming to the end. I want to thank everybody for participating today, and thank Vladimir for giving us this talk.